Now let me give another construction of a measure called the Lebesgue-Stieltjes measure on the real line, which uses the Hahn Kolmogorov extension theorem. So for this we define what's called a monotonically non-decreasing function So a function f from R to the positive reals, rather extended positive reals, is called monotonically non-decreasing if fx is less than or equal to fy whenever x is less than or equal to y. So it is a monotonically non-decreasing function. So define for a monotonically non-decreasing function for f monotonically non-decreasing, the following two quantities, which is for x in R, we define f minus x to be the supremum of values fy, where y is less than x, strictly less than x, and f plus x is the infimum for values greater than x, y greater than x for the values fy. And we have f minus x is less than or equal to fx is less than or equal to f plus x, because f is monotonically non-decreasing. So using this function capital F, we will define a pre-measure by giving a formula for the pre-measure on bounded intervals. Now we can define what's called the Lebesgue-Stieltjes elementary measure. So this is defined as follows: for any number, real number a, we have, so I'll denote this as mu f of the singleton set A. This is by definition f plus a minus f minus a. So in contrast with the elementary measure where we had the elementary measure of the singleton sets were 0, but here they may not be 0. So the Lebesgue-Stieltjes elementary measure gives may give a non-zero finite weight to a singleton set. Now using this, we can define for finite numbers a and b, define for the open interval a b. This is by definition, because it is an open interval, this is the open interval a b. So we would like to approach a from the right and approach b from the left. So then this Lebesgue-Stieltjes elementary measure is given by f minus b, because we are approaching it from the negative lower values of b, and we are approaching it from the higher values of a, so there should be a plus sign, and so minus f plus a. So this is the formula for the Lebesgue-Stieltjes elementary measure for an open interval. And now we can deduce for any other interval which contains the endpoints just simply by adding the value of the singleton set. So mu f of a b this is equal to mu f of A plus, again by definition, mu f of AB, and this is f plus A minus f minus A plus f minus B minus f plus A. So this gives us the value f minus B. So f plus A and minus f plus A cancel out, so f minus B minus f minus A. Similarly, we can do it for other cases. Mu f of A, B, with B, the endpoint B included, this is going to be mu f A B plus mu f of the singleton set B, and this is nothing but again f minus B minus f plus A plus f plus B minus f minus B, and then f minus B and f minus B cancel out, so you get f plus B minus f plus A. So one can simply try to memorize these formulas, but it's better to just memorize two cases. First is that one for the singleton set, this formula, this is for the singleton set, and for the open set, and we have the idea that if you have an open set, you approach from each endpoints from within the interval. So the higher endpoint you approach from the left and the lower endpoint you approach from the right. So conceptually, if you understand these two cases, then you can derive all the rest of the formulas using some kind of finite additivity law imposed on these elementary measures. So then I will just write down one more case, which is when both endpoints are closed. So this is again mu f A plus mu f open interval A B plus mu f of the singleton set B. So this is f plus A minus f minus A plus f minus B minus f plus A plus f plus B minus f minus A. So many things will cancel out. For example, f plus A and f plus A cancel out, and then so this should be f minus B here, and then here f minus B and f minus B cancel out, and you are left with f plus B minus f minus A. So therefore we can derive all these formulas for the elementary Lebesgue-Stieltjes elementary measure. Now we can extend the formula for the Lebesgue-Stieltjes elementary measure to half infinite and even infinite intervals of the form. So first also we have f plus of plus infinity is equal to plus infinity, f minus of minus infinity equals minus infinity, and f minus of plus infinity, so there is no set here, it's just plus infinity and minus infinity, and here f minus of plus infinity is the supremum, because we are approaching from the infinity from the left, so it's the supremum of all y of fy, values fy, and when you approach minus infinity from the right, then you should get the infimum of all values fy. So using this we can then define mu f for half open, rather half infinite intervals of the form a plus infinity or minus infinity a and so on, and even minus infinity plus infinity. So we can use the exact same formulas we have used before, just by taking these values for f minus and f plus on plus and minus infinities, and then using the obvious convention, such as if you take such as plus infinity minus infinity is going to be plus infinity, and so on. So we have defined it for bounded intervals as well as unbounded intervals. Now we can define the elementary subsets of RD. These are finite unions. So E subset of RD says that E is a finite union of bounded and half infinite intervals, or the complement is a finite union of bounded and half infinite intervals. So this gives us a new Boolean algebra. So one can check that this is a Boolean algebra. So I'll write a lemma and leave this as an exercise for you to show. Lemma that EFRD, well, this Boolean algebra doesn't really depend on f, so E bar RD is with the measure mu f is a pre-measure space, meaning that this is a Boolean algebra, and mu f is a pre-measure on this Boolean algebra ERD. So the difference between this one, so I should change the notation because this is not quite the elementary algebra as we have defined it. So let me write E prime throughout. So but still one can try to compare E prime with the elementary algebra E. Nevertheless, you have a pre-measure mu f on this new Boolean algebra, and so the Hahn Kolmogorov extension theorem, Hahn Kolmogorov gives a measure, a sigma algebra, which let me call it LFRD, and a measure which I continue to call mu f, which is called the Lebesgue-Stieltjes measure on RD. So in particular, if a particular example of a Lebesgue-Stieltjes measure is if f is equal to the identity map, then this mu f is nothing but the Lebesgue measure. So all these are exercises for you to check that. First, the lemma says that this is a Boolean algebra and a pre-measure, and then the Hahn Kolmogorov thing gives you a Lebesgue-Stieltjes measure, and for the particular case of the identity map, this gives you the Lebesgue measure. So here this one subtlety here is that I defined it for a monotonically non-decreasing function which takes positive extended positive real values, but I should actually try to replace this by r. So if you have a monotonically real valued non-decreasing function, then you can define the whole thing, and the identity function is then admissible here as a monotonically non-decreasing function. So then you will still get mu f here is taking values in the positive extended real numbers because of the because f is monotonically non-decreasing. So mu f on intervals or half infinite, so finite intervals or half infinite intervals gives you a value between 0 and plus infinity. So it is a first one has to check that it is a finitely additive measure, then one has to check that it is a pre-measure, and then for the particular case of the identity one should check that you get nothing else but the Lebesgue measure.